getting into, chapter 14, getting into section 3. This is the last section of chapter 14, and we're going to be talking about another type of transformation that we call a dilation. Okay, so if you are familiar with going to the eye doctor, for example, they dilate your eyes. It's sort of the same concept. You know, they put a drop in your eye and it makes your pupil get bigger. Well, that's what a dilation is. So we've been talking about isometries, and they preserve distance. So an image under isometry is congruent to the original figure. Okay? But a different type of transformation that's not in isometry, because the size is going to change, would be in a dilation. So we could see this by thinking about projecting an image onto a screen. For example, when we're in the classroom, if I use the PowerPoint, well, I have a small iPad screen that my PowerPoint is on, and I project that onto the screen, and you see it as the same image but bigger, right? And so that is a dilation. And so that's what we're talking about. We're talking about changing the size proportionally so that it's the same shape, just now bigger. Okay? And so as we talk about dilations, that's one thing that we are going to be looking at is this idea of taking one image or one original figure that is maybe small and then making it bigger, or we could even take a big image and make it smaller. And so it's this idea of changing size, but not shape. Shape is going to be preserved. So you can see, if you take this image here of this boy, and that's the original, if you project it onto the screen with a scale factor of 20, meaning it's 20 times bigger than the original, then you would have this image that you see on the screen. And so that's how a dilation works. It's taking that small image, keeping its size, and doubling its size, and keeping its shape, doubling its size, triple its size, multiplying its size by 4 or 5, or in this case 20. So I've talked to you throughout the videos of this chapter about if you were to teach some of these things in a class, whether that's an upper elementary class or even in a geometry class at the high school level, there's some really neat and fun activities that you can do with each of these transformations. And one of my favorites that we did when I taught at the high school level, teaching geometry, is we would do a dilation. And so I would have my students pick out one frame of a cartoon in the newspaper. Okay, so you have this one frame. It's a square, rectangle, could be either one, doesn't really matter. And I would make them draw off in that maybe half centimeter by half centimeter grids. So it kind of looks like this. And when they would get that grid, they would then take that distance. So let's say that each of those squares is a half centimeter by half centimeter. They would take a piece of notebook paper, and sometimes they would do it on poster board paper or poster board, and they would multiply that half centimeter by 2, 3, 4, whatever. And so maybe they multiply it by 4 and they get 2 centimeters in this new grid paper. And so you would have the same number of squares or rectangles, and what they would do is they would take whatever's in this first box and they would draw it into this box, and then they would take whatever's in this second box and they would draw it into the second box, and so on. And they would do that across the whole picture, and when they get done, they've taken this cartoon and they've blown it up into a bigger size. And you always had students that said, well, I can't draw. Well, even the people that said they couldn't draw, theirs turned out to be really, really neat. Really good drawing, because they were just drawing piece by piece. And so that's a way that you could have your students form a dilation, is by taking this small cartoon and blowing it up. I did one time. I was coaching baseball at the time, and I found a cartoon about baseball. And so I took it and I put it on an overhead projector, kind of like what you see here on the screen, and I blew it up really big, and then I traced it. So I sort of cheated, but I traced it out so that mine would be a much bigger scale than my students were. But I could put that up in my classroom. And so I put it up, and they were able to see, okay, here's what we did with ours, here's what it should look like. And so it really kind of brought this idea of a dilation to life. And so I would take my original, and I would maybe tape it down here in the corner, and they could see, oh, wow, it went from that to now this large, same exact picture, but bigger. And so that's the way a dilation is going to work. So in a dilation, we want to talk about how does it change. Does the size increase by 2 or by 3 or by 4? And the way to do that is to figure out in the original figure the length of your sides. So in this case, from A to C, that segment is pretty easy to see. It's 1, 2, 3 units long, right? And you can see in the image from A prime to C prime, it's 1, 2, 3, 4, 5, 6 units. And so this original triangle was multiplied by 2, or we doubled the size. And so now the new triangle, the new image, is twice as big as the original. And we say twice as big because, again, the side lengths. And you can do the same thing with CB. So it's 1, 2, 3 units. And you'll notice that C prime, B prime, that segment is 1, 2, 3, 4, 5, 6 units. Again, it's been doubled. Okay? So when we talk about this dilation, that's what we mean. Did the side lengths get twice as long, 3 times as long? Did they get shorter, by a certain scale? And so we're talking about this idea of blowing up or shrinking this image or this original figure. So here's a formal definition. A dilation from the plane to the plane with center O and scale factor R, so that's what we're multiplying by, is a transformation that assigns each point A in the plane the point A prime such that O, A, and A prime are collinear. O is not between A and A prime. O, A prime is equal to that scale factor times the distance of OA. Now, that probably doesn't mean a whole lot to you. Essentially what it means is that if we have, let's just start with the segment. If we have this segment and we want to increase its size or decrease its size, either one, then we would have this point O, we'll call this P and this P prime. And what it's saying is that if we want to dilate that, make it longer, then we could have, again this is O, we could extend this line to where we have OP and OP prime, and so we can compare those two together. Okay, we use P and P prime, not A and A prime, but it's the same concept. And so it's this idea of side lengths expanding, getting longer, and that's going to tell us how much bigger the image gets. So let's look at some examples. Now, before we get into our first example, I do want to point out it is possible that you can go in the negative direction. You can get smaller, right? You can have a negative scale factor, meaning that if, instead of saying, oh, this image is twice as big as the original, we could say it's cut in half, or it's 2/3 the size of the original, or it's 1/4 of the size of the original. And so you can talk about that scale factor as getting smaller. It's not technically negative numbers, but it is a smaller image. And so it's not always that we blow it up and make it bigger. That's typically what happens, but sometimes it could get smaller. All right, so here's our first example. We want to find the image of the quadrilateral ABCD under the dilation with center O and a scale factor of 2/3. Now, here's what that means. And I'm going to use a ruler to do this. If you have a ruler, I would encourage you to get it out and try this on your own paper. So what we're going to do is we're going to draw a line from O to each vertex. So for example, O to B would be there. So if I can do this without messing my screen up here. From C to O would be there. From A to O would be there. And then we'll do D to O, which is there. Again, it's slightly off, but close enough that you can get the idea. Now, why is this O important? Well, this point O is going to be that center around which our dilation happens. So if we're making it smaller, so 2/3 is smaller than 1, right? So we're going to make a smaller figure. We're going to make it smaller going towards that point O, okay, going in this direction. So how do we figure out the factor of 2/3? Well, if you take, let's start with DO, this segment here at the bottom. If you take it and split it into 3 equal parts, and we're doing 3 equal parts because of the thirds, this denominator of 3. And we want our new image, our new figure, to be 2/3 the size of the original, right? We have the original, we want the new one to be 2/3 of that. And so that means that this side length needs to be 2/3. And so there's 1/3, 2/3. So point D prime needs D, not P. Point D prime needs to be here. Well, I did a P again. There we go. D prime. And then we'll do the same thing with all the other segments. So with AO, if you split it, and this is not going to be exactly accurate because it is an estimation, point A prime should be there. And if you do the same thing with BO, you split it into 2/3, point B prime is going to be there. And if you do CO, it's a longer segment, split it into 3 equal parts, you're going to have point C prime that's somewhere like that. And then if you connect all those vertices, so there's one, there's one, there's one, and there's one, we now have that same shape, that same figure, but it is 2/3 the size of the original. Now, I'm going to use the technology we have here to put that image in place and see if it matches mine. Mine's pretty close. All right, you can see the one in blue, that is what it should look like. Again, my points are slightly off. Again, it's an estimation. It's going to be slightly off probably at times. My point B is exactly on. Point A is slightly off. Point C slightly off. So is point D. Again, when you're estimating the 2/3, that's the case. Now, if I had taken my ruler and I had measured segment BO or segment CO or segment DO or AO, then I could have found the exact length and then divided by 3 to get it in 3 equal parts. But I didn't. This is, again, an illustration of how we would use that scale factor. Now, think about it going the other way. What if I had told you that we wanted to have a scale factor of 2? Well, we would then have extended, let me do it in a different color. We would have extended this out to make it twice as long as DO. And so maybe point D would have been there. And we would have extended this segment to be twice as long as CO. And so maybe C prime would be there. This would be, we'll call it double prime. Put 2 marks. And then we could have done the same thing with point B, extended it out to maybe right in that area. We'll call that B double prime. And then with point A, or that segment with A, we could have extended it out, double the length, and maybe it was here. We call that A double prime. And so you could have taken this same figure and you could have used a scale factor of 2 to get this shape. That would be twice as big as the original. So this is times 2, or twice as big. This one, the original one, was 2/3 times 2/3 the size. Okay, so just to kind of show you how that would work, if you project it out bigger, then you get this bigger one, obviously. And if you do the scale factor of 2/3, then you get the one that's on the inside, that smaller one. If you have any questions about how to construct that and draw that, let me know. Again, this should be a pretty good illustration for you of how a dilation actually works. So, a dilation with center O and a scale factor of R has the following properties. There's a couple properties here. The image of a line segment is the line segment parallel to the original segment and R times as long. So if you go back and you look at this one, let's say this D double prime O, so this segment here at the bottom, we extended it twice as long, right? So a scale factor of 2. And if you were to pull that whole segment out, it would be parallel to DO, this original here, right? And so that's what this is referring to. The line segment would be parallel to the original and R times as long. Also, the image of an angle is an angle congruent to the original angle. Well, and that should make sense, because if you look at this example, well, this angle here from B prime, A prime, D prime, well, it's going to be the same angle measurement as BAD, right? You can see, hopefully, those appear to be the same angle measurement, okay? This one, this other one where I blew it up times 2, it's a little off. It too should be a congruent angle, because that shape is going to stay the same. It's just the size is changing. And so that's what that property says as well. Again, if you have any questions about this, let me know. All right, so look at this one. So we want to show that triangle ABC, so that's the bigger one that you see here, is the image of ADE, so that's the smaller one, that's this one in here, under a dilation. And we want to identify the center of the dilation and the scale factor. So we can see that this bigger triangle, ABC, appears to be blown up from the original, right? The original being ADE, okay? So the question is, well, what's our scale factor? Well, how much does this side here change? Well, originally it was AE, which is 1, 2, 3 units, so it has a length of 3. And now AC has a length of 1, 2, 3, 4, 5, 6 units. So now, from there to there, 6 units. Well, how did it change? Well, it changed by multiplying by 2. And if you look at AD, it's 1, 2 units. And then from there to there, from A to B, is 4 units. So how much did it change? Well, again, it was multiplied by 2. And so our scale factor here is 2. Now, where's the center of this dilation? Well, it has to be at point A, because point A didn't change, right? We just extended the sides out, with point A being our center point, which is the order pair 1, 1. And so what we're able to do is to show that this is a dilation you compare those sides. So AB, which is this side here at the bottom, divided by AD gives us 2, right? So 4 divided by 2 is 2. Same thing is true with AC and AE. AC is 6. 6 divided by 3 is also 2. And so that scale factor then is a 2, and our center is at point A, because again, that point didn't change. We didn't move it anywhere, right? So point A is our center, and it, from that point, expanded out 2 times the length that it was. And so that's what all this here at the bottom says. That tells us the answer. But I want you to understand, how do we show that? How do we show that it's a dilation? Well, we have to show that it changes proportionally. For example, if we were to take, let's just say another triangle like this, and we were to have another triangle that looked like this, for example, well, that's not a dilation, right? Because this length and this length are not going to be proportional to this length and this length. And so you have to show that everything is changing the same proportion, in this case, changing by a scale of 2, where here that doesn't work. Okay, so just to help you kind of see how do we show it's a dilation, we have to show that everything is proportionally increasing or decreasing. Again, if you have questions about that one, let me know. All right, so some applications, and this is another thing that you can do with students that's really a fun thing. I actually talked to my son the other day. He's in 4th grade, and he and my daughter were drawing pictures and doing some things, and we actually talked about perspective drawings to him. Because in a perspective drawing, you take that center point, that O that we've been dealing with, and you use that to draw everything towards a point. And so when you do, it gives you a 3-dimensional image. So, for example, to make a letter appear 3-dimensional, we can use a size transformation, so a dilation, with an appropriate center O and a scale factor with selected images to create a 3-dimensional effect for the letter C. So I'm going to show you in the next slide what it looks like. But let's say you take the letter C, and let's take a block letter. I'm not very good with block letters. And let's say that, there it is. Let's say that point O is here. So we would take a line from each of our vertices out to that point. And then if you draw that again, let's say halfway between each of those segments, those dotted segments, and you redraw that C, again, not great at that, then you would begin to see that we have a 3-dimensional image here. And so you can see that C is expanded. We've stretched it out towards that point O. And so it would look like this if it's done accurately, where you do expand that out. So I did a bonus activity one time, I guess several times in my geometry classes when I was teaching high school, and I would have students draw a drawing using perspective drawing. Okay, so what we would do is, there's 2 different types of perspective drawing. We're not going to get into those really, but there's a 1 perspective and there's 2 perspective. 1 perspective typically is where you have a point towards the center of your page and everything kind of goes towards that. Where 2 perspective, you have a point on each side of your paper and everything on the right side goes towards the one on the right and everything on the left side goes towards the one on the left. So you could have, if you did 1 perspective, for example, so let's just say there's our point O. Well, if I wanted to draw a road, and I wanted to look down that road, and you've seen this in movies and different things, maybe you've seen it just driving down the road, where you look straight down the road, and it looks like everything goes to a point. Well, we can actually draw that out. So if you were to draw this, where if you were to extend these, they would go up to that point. And then you can do a dotted line here in the middle and then take out this part. Well, you can see that that road then, that picture of that road, is going to go towards that point. And let's say you want to put a building here. Well, you can put that building going towards this point. Again, not continuing that. And then you could draw a vertical line here, and then this point going, or this line going towards that point. And maybe you have, let's see, again, just kind of off the cuff here, drawing a picture. And so you could begin to see how a 3D image takes place, right? Because everything is going towards that one point. And so when that happens, you can have a really neat 3D drawing. And so there's a lot of examples. I don't know how many there are in your book. I don't remember seeing a ton of those in your book. But you can actually Google perspective drawings, and you would see a lot of those. They can be really elaborate. They can be not very much to it, kind of like this road with a building beside it or something. So it can be really, really neat when you look at that. But this is a way that dilations are used quite often. Again, from an artistic standpoint, if you have students that are artistic and really into art, this is a great way to get them involved and get them invested in this topic, because you can allow them to actually do some of those creative things. Don't put a limit on what they're able to draw, and just say, use perspective drawing, and let them just have fun with it. And so that's a way that you can get your students really invested into your class. Cool. All right. So what we're going to do here, we're almost done with this chapter. We're going to show that triangle ABC, so that's the one in blue, is the image of APQ under succession of isometries with a size transformation. So remember, our isometries, we can translate where we slide, we can rotate, we can reflect, and then this size transformation is the dilation. So if ABC is going to be the image of APQ, then angle P and angle B need to match up. And angle C and angle Q need to match up. And so let's think about this for a second. If I need this one, a little squiggly circle around it, to match that one, then I need to get this angle Q to the top, right? And so the way we can do that is to rotate it. If we were to rotate it, then this one would go up here, and this one would go up here. Excuse me. And you would get a rotation, a half turn, where it's being rotated 180 degrees. And you would then end up with, since AQ is 3 units, point Q would go there, and point P would go here. And so this would be your triangle under that rotation. Still a congruent figure, right? And then we would want to take that and expand it, the size transformation, when we blow it up. And each side length is changing. So this is 3 units, and then 4, 5, 6 units. And then same thing with AP, it's 2 units, and then AB is 4 units. And so each of those size transformations, or those side lengths, are going to expand double their length. So a half turn rotation So a half turn would give us the triangle I've drawn in red. And then a dilation with a scale factor of 2. So that's how we would get that new triangle. So you can see that here. In fact, the one, they've actually put one in red there. If I erase mine, you'd be able to see that. So to transform APQ by half term, we'd get A P prime Q prime. And then C is the image of that Q prime under dilation. And B is the image of P prime under the dilation. And so we end up with the half turn and the scale factor of 2 to get the image. Again, if you have questions about that, let me know. It's just a matter of applying each of these and figuring out how much does it turn, rotate, expand, decrease, whatever. And that's all we're doing here. We're just trying to show that we took the original figure and did stuff to it to get that image. So you can see how that went. So this APQ was the original. The one in red, A P prime Q prime, is after the half turn rotation, and then the blue one, ABC, is the image after that scale factor of 2 has been applied. And in that scale factor, in that dilation, A is the center because point A doesn't move, right? We're not moving closer to or further away from that point. That point is still fixed, and so that must be the center. And so our last thing here, two figures are similar. Okay, so we've talked about congruent a lot. Similar means that the two figures have the same shape, not necessarily the same size. So two figures are similar if and only if it is possible to transform one onto the other by an isometry or sequence of isometries followed by a dilation. So notice what happens here. If you, in the previous problem, when we took this original triangle, the one in black here that you see, when we took it and we rotated it and then we expanded it, this ABC, all the angles still are the same. So if a figure is congruent, all the angle measurements are going to be the same length or same size. It does not mean that if the angles are the same size that it can't be congruent. It just doesn't guarantee that. So earlier in chapter 12, I guess it was, we talked about side, 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 angle, side, angle, side, angle. We talked about all those different ways to tell triangles were congruent. Same angle measurements and then same side lengths. Here, this tells us that we have similar objects, and that's different than being congruent. Okay, similar means it's the same shape, not the same size. Okay, and so based on all these transformations, that is the final thing that we can say about similarity with isometries and dilations. This does finish up chapter 14. If you have any questions, let me know. Again, this is chapter 14 in your book. On your math lab, it's chapter 13. So be aware of that. I'll post an announcement so you know that. But this does finish up this chapter. If you have any questions about this chapter, make sure